In this lecture, I am going to discuss on QPSK waveform and its drawbacks. In the last lecture, I have discussed QPSK modulation scheme, digital modulation scheme, and in that lecture, we have seen the constellation diagram of QPSK. So the constellation diagram looks like this. You have the two carrier components, the in phase component and the quadrature phase component sin omega t, and you have the 4 points in this constellation diagram, and this point is mapped onto the bits 1 1, and this is mapped onto 0 1, and this is 0 0, and this is 1 0, right? And whenever one comes, you transmit this point with a phase degree of 45 degree. By the way, this 45 degree is measured with respect to cos omega naught t, and this one is going to be 90 plus 45, 135 degree phase shift, and this is 225 degree phase shift, and this is 315 degree phase shift. So this is what we have discussed in the last class. So therefore, there are 4 possible phases which can be transmitted based on the incoming bit stream. So those phases are either you transmit 45 degree or 135 degree or 225 degrees or 315 degrees. Okay, maybe I can take some other 4 phases also, like 0 degree, 90 degree, 180 degree, and 270 degree. Okay, so it doesn't matter qualitatively, okay, whether you take 45, 135, 225, 315 or 0, 90, 180 and 270. Okay, it does not affect the argument qualitatively. Okay, now let me take the waveform, how it looks like. Let me draw the waveform. So this is a duration of t seconds. 1 cycle, again 2 seconds, another cycle, then I have 180 degree phase shift, then 90 degree, then 1 cycle, and then half cycle, like this. Okay, now this duration is symbol duration capital T, and this also symbol duration of capital T, and here this also symbol duration of capital T, and so on so forth. Okay, and this also capital T symbol duration. Now if you notice here, in this interval, the waveform has 0 degree phase shift, and this also, and 1 minute, this also 0 degree phase shift, but at this point if you notice, there is a phase shift of 180 degree. Okay, so here in this location I have 0 degree phase shift, and here also I have 0 degree phase shift, but here I have 180 degree phase shift. And if you look at this point, let me take this one, red point. If you note down this point, I have a 90 degree phase shift. Okay, I have got a 0 phase over t seconds. Okay, this t seconds corresponds to, here capital T corresponds to time for 2 bits, or time for what is something called a die bit. So you can call die bit or 2 bits. Therefore the bit period, it is denoted by TB, which is going to be capital symbol period by 2. So you are looking at die bits, that is 2 bits together, and then transmitting one phase of the carrier. So you wait 2 bits and then decide what phase that you are going to transmit. Okay, therefore I can have 0 degree phase shift, phase transition, or 180 degree phase transition, or 90 degree phase transition, or 270 degree phase transitions. Okay, so now what you will find is every t seconds, every symbol interval, there is a possible phase change. There may be a phase change, there may not be a phase change, depending on the successive bit combinations that you get. So what are the values of the phase change that you will get in this waveform are 0 degree, 90 degree, 180 and 270. What is the maximum phase change that you can get? Well, you can say 270 degrees. Again, this 270 degree is something called minus 90 degree. If you take the magnitude, because we are considering only magnitude, if you take magnitude of this, again it is going to be 90 degree. So essentially when I say 270 degree, it indicates 90 degree phase shift only. I mean minus 90 degree. Again, if you take modulus, it is 90 degree only. Therefore, I cannot say maximum phase change is going to be 270 degree, but I can say 180 degree phase change. Therefore, in the QPSK waveform, there is a chance or there is a possibility that 180 degree phase changes can occur, either plus 180 or minus 180 in magnitude. So you can have as large phase changes as 180 degree at the points of going from one die bit to another die bit, or one symbol interval to another symbol interval. So essentially means that in reality you will never get rectangular pulses no matter what you do, because each die bit is denoted by a rectangular pulse in the baseband modulation, right? So if you have this 180 degree phase transitions, then you will not get a rectangular pulses, because the rectangular pulse needs an infinite amount of bandwidth. If you take Fourier transform, then you will have a sync pulse, and the sync pulse, we know that it has infinite bandwidth. So when you do a band pass filtering of such a signal, before you finally transmit it onto the channel, you will go through a zero amplitude. The envelope really goes to zero here. Okay, so the envelope perhaps stay constant here in this point, constant. In this point, constant. Okay, but at the phase discontinuity, what will happen? Your filter will completely remove those phase discontinuity. Okay, and therefore in the spectral domain, you are removing some component. Essentially, if you remove some components, then if you look at the corresponding waveform, maybe I'll take up to this point, and here also I'll take up to this point. If you look at the corresponding waveform, the time domain, it may not be a rectangular pulse, it is a smooth rectangular pulse. See, here you have the constant, maybe I'll draw a little clearly, like this. You have the constant amplitude in this point, and here there is no constant. So the transition is not sharp, it is not, it is not abrupt. So in such a case, what will happen? The decay will not be abrupt one, okay, but a rounded one. So normally you can think of a QPSK signal, or you think of a QPSK signal as a constant amplitude signal. Because of this, no abrupt transitions, it is no longer a constant amplitude signal in the QPSK system, and that is not a desirable thing to have in any communication systems. Okay, so the desirable thing in a communication system is a constant amplitude signal. Constant amplitude signal. So whenever you have phase discontinuities, and that phase discontinuity will tend to be smoothened out by the filter, because you are passing through a filter, and that filter is a band limited one, and that will remove in the time domain, the equivalent effect is smoothing out the sharp transitions. Okay, so by making the waveform rounded edge instead of a sharp edge, so the transition will not be abrupt one. Therefore, you don't get a constant amplitude envelope signal in the time domain. In case if it is not constant, then what will happen? So it will create some problem. That's what we are going to look at now. If it is not constant amplitude, then there are two problems we need to address. Okay, so therefore a constant amplitude signal in a communication system is a desirable property. Okay, the reason why it is desirable is, the one is from the power amplifier perspective. Power amplifier perspective. We know that power amplifiers through which we are going to send the signals, okay, and that power amplifiers will work more efficiently at a specific level of amplitude or power, rather than having a large dynamic range of variations. You have a power amplifiers, and you have the input signal x of t, and if this input signal has very large dynamic variations, okay, it keep on varies from one level to another level in amplitude, then what happens, your power amplifier will not work more efficiently. So therefore, if you allow a large amplitude variation in the amplitude, then its efficiency will come down. So this is one reason. Therefore, you should not allow large variations in amplitude. So you maintain the amplitude within a certain limit as possible as. That is one reason by a power amplifier point of view. And the second reason is non-linear effect. Non-linear effects. Okay, so this non-linear effects will be more pronounced when the envelope is not constant. Okay, whenever the envelope is not constant, then this effect will come into the picture very severely. If there is a non-linearity in the system, then the system will respond with different gains at a different input amplitude levels. That is the main drawback. You have the non-linear device, non-linear system or non-linear block in the communication system. You have the input signal. Now what happens, for each input it gives a different gain that is undesirable. Whatever the signal you are giving, the amplifier or any system should give the uniform gain. The same gain should be given for all amplitude levels, but that will not happen. So this is something undesirable property. So different undesirable property, and so it is best to have a constant amplitude of operation. So in that case, you have to maintain the input at some constant amplitude level. So you are going to work at a specific point on your non-linear system, and around which you may expect a linear kind of behavior without any problem. So that is why both in non-linearity presence point of view as well as efficient power amplifier point of view, it is preferable or desirable to have waveforms with a constant amplitude in any communication systems. So this is a very important thing. So the QPSK signal to start with looks like such a constant amplitude waveform, but in reality after filtering that will not going to work. It is no longer remains constant, which means that you are likely to have non-linear problems due to the non-linear device, non-linear effect from the non-linear device, also power efficiency problem. So this is something we should keep in mind. Now how can you overcome these two drawbacks? So these two drawbacks we need to overcome. So what is the things? So in the research community they have done many things, they have tried a lot of things, and they come up with a very simple and straightforward improvement one can do, and that is, what you do is, in QPSK you wait for 2-bit intervals, let's say 0 0 or 1 0 1 1 like this. 2-bit intervals you will wait. That means t seconds you will wait, and then you take a transition. Okay, you decide based on the successive bit intervals, you take the transitions, either 0 degree transition or 90 degrees transition or 180 degrees transition or 270. So instead of waiting for t seconds, you take a transition at every half of t symbols, every half of every half of symbol duration. Okay, that is you are offsetting the symbol duration t by 2, that is t by 2. So this is called the offset QPSK. So now the new phase transition will occur at every tb by seconds, because this t by 2 is going to be t sub b, bit duration. So therefore in this case phase transition will occur at every tb seconds. So here this scheme is called offset QPSK. The dictionary meaning of offset is reduce. So what we are reducing here, what I am reducing here, I am reducing the bit interval, or sorry, duration of the pulse. Duration of the pulse. So in QPSK, the duration of the pulse is t seconds. Okay, and maximum phase changes plus or minus 180 degrees. Now in the offset QPSK, duration of the pulse is pulse is TB seconds. That means T by 2 seconds. Okay, therefore what happens? The phase transition max plus or minus 90 degree. Okay, so the phase discontinuities is somewhat reduced by OQPSK, and this non-linear effect and power efficiency problem is reduced to a certain extent. Therefore OQPSK is considered as a child of QPSK, and it has slightly more desirable properties than QPSK in this manner. Okay, so at this point I'll stop in this lecture. In the next lecture we will continue offset QPSK scheme. Thank you.